my brain.
Over here, we're looking for what parts of your brain were activated when you were trying to time the duration of those stimuli.
Warren, look at this. This is by far the brightest part of the timing part of the brain. What's happening there?
Well, this is the front part of your brain where the critical part of the stopwatch is.
It's astonishing. I'm looking at the very cells which sense time passing, seeing them in action.
So this is what's beating then, right? There's a stopwatch is right there.
Right.
Now, what's inside there that is actually beating? Is it a chemical reaction? Is it a nervous reaction? And what is it inside there that's clicking away?
Right. Well, there are thousands of brain cells inside of there that beat in a regulated fashion, and they serve as essentially the tick-tock of the stopwatch.
So even this sense of time passing is embedded within the neurochemistry of our brains. A cluster of cells near the base of our brain releases a chemical that acts as a start signal. This then triggers a group of neurons at the front of the brain to fire together, but each to a different beat. And it's this pattern of beats that signals how much time has elapsed. This process is happening constantly, without us even knowing it. We're continually timing the world around us.
So if Warren is right, it means that he's been able to isolate the circuits that allow us to judge the passing of time. The organ, so to speak, that allows us to measure the beat of time itself.
The discovery of the stopwatch might even explain a bizarre phenomenon. In life-threatening situations, people say that time slows down, so much that they could see every tiny detail. The question is, does time really slow down, or is it just imagined? We're going to find out. Psychologist Dr. David Eagleman is about to conduct the first ever scientific experiment to explore whether time really does slow down in a near-death situation.
So in order to measure how fast people's brains are taking in information, we've built this device, which we call the perceptual chronometer. And the idea is that numbers flash very rapidly on this LED screen. They flash so rapidly that a normal brain under normal circumstances can't see what's being flashed here. But if time were running in slow motion, then you should be able to distinguish the numbers.
Jesse Callis has volunteered to be our guinea pig.
Can you see that there are numbers flashing on the screen here?
Yes.
Okay, these are flashing at a slow rate. If I
Okay.
speed this up, at some
First,
point...
David has to make sure that Jesse can't read the numbers when time is running normally for him.
That it's very difficult to read what the numbers are. It would be
Yes,
impossible.
very difficult.
Okay, and so are you able to read what's on the screen now?
Yes.
How about now?
Yes.
Okay. And here, can you read the number at all?
No, not at all.
Okay.
Let's just do this number here.
Yeah, great. Is that too tight?
No, go ahead.
Okay. There's no way to fake this test because if time is not running more slowly, they can't see the sequence.
Nervous.
It's a long way down.
Hold on. Just good.
Jesse is about to free fall from a height of 33 meters, 12 stories above the ground. The question is, will he be able to read the number on the way down?
It's great.
Jesse, did you see any numbers on the display?
Yeah, 56.
56, all right, let's verify this. Okay, the number that was actually presented was a 5 and a 0, 50. The 0 happens to look a lot like a 6. So what this means is that, at least mostly, he was able to see a presentation rate that he was not able to see under normal circumstances. Maybe what we can do is try again and see if you get both the numbers right this time.
Again?
Again.
Okay.
Hey, how you doing? So watch your head on the side, facing.
I find this result fascinating. I would have loved it if he saw both numbers exactly correctly, but this at least suggests to me that he's able to take in information faster than he was before.
'96.
96? True.
That's what I saw.
The answer is 98. Hey, that's great.
So for a second time, Jesse has seen a number very similar to the one on the screen.
These results today are very encouraging because this is the first evidence that somebody's brain can speed up and they can see the world more slowly during a high adrenaline situation.
This is the first demonstration that time really can slow down. But how? Back at Duke University, Warren Meck is exploring this remarkable phenomenon by giving mind-altering drugs to rats.
We're particularly interested in drugs like cocaine and marijuana because we believe they can distort time perception by compressing time or lengthening time. Hi, Red. Is everything ready?
Hi, Ron. Yes, everything's ready.
Good, let's go.
He's going to test whether these chemicals change the stopwatch mechanism that allows the rats to measure time.
So the rats have had their drugs for about 20 minutes now. As you can see, the marijuana rat is mellowed out. The cocaine rat's gotten quite mad and is trying to escape out of his cage here. And the saline rat is just acting normally.
The plan is to give the animals a timing task. The rats have previously been trained to measure time precisely. If the rat presses a lever after 12 seconds, he gets the reward of a food pellet. But if he's too early or too late, he gets nothing. The rat, given saline only, does this task perfectly and presses the lever after 12 seconds, the correct time. Next, the rat on cocaine. For this rat, time seems to zip by. It presses the lever after only 8 seconds. And lastly, the rat on marijuana. Here, time seems to have ground to a halt. This rat doesn't press until 16 seconds have passed.
So overall, we're seeing a modulation of the stopwatch where we can speed up the stopwatch and slow down the stopwatch, or we can maintain normal speed under control conditions.
So it seems that our very real experience of time speeding up or slowing down can be directly influenced by chemicals. And this could account for what's happening in the free fall. Under high stress, we release adrenaline, and this, just like a drug, affects the chemical pathway of our stopwatch, slowing down time. It seems that even our sense of time passing, something that seems so much a part of the outside world, is an internal process, a fundamental part of our psychology.